Point bringing damage to your burrow. We some brothers from the east with them beats that be thorough. Got the solar gravitation, so I'm bound to pull it. I gets down like brothers of.
Okay, so now I'd like to go over some properties of the cross product. Properties of, and I'll just write this, of the cross product. Okay, so the first one is pretty important. I mean, all of these are important, but the first one especially, you'll see, and perhaps even in like physics classes, you might see this as well. So V cross W, and this refers to the resultant vector by crossing two vectors. Like in the last one, it was -3, 22, -7. So that final vector there is orthogonal. And again, orthogonal just means perpendicular to both V and W. V and W. This does not imply that V and W have to be perpendicular to each other, but it's just saying that if you have V here, so let's say this is V and this is W, okay? These don't have to be perpendicular, like I said, but let's say they form a plane, right? Any two vectors form a plane, okay? And a unique plane. And then, so if we have V and W here, our cross product is going to be orthogonal to it. So it might like point down, but it's going to be normal or perpendicular to the plane, okay? So this is our V cross W pointing down there. All right, so now for the next property. So number 2, it's going to be that the magnitude of V cross W of our resultant vector is equal to the magnitude of our original vectors multiplied times each other and times the sine of the angle between them. Okay, so theta is angle between V and W. Okay, all right. So this one will go into more detail in the next topic that I cover. But anyways, moving on. So number 3 says that vector W, and our resultant V cross W vector, this forms a right-handed system. Right-handed system. Okay, so what this means, you might be like, okay, so what does this have to do with my right hand at all? But basically, this has, well, just in general, math has a lot of applications in physics. But for a geometrical or physical interpretation, it just means that if you have V and W, so let's say here's V, okay, so here's our vector V, here is W, all right? If you put your, let's see, your index, or like your whole hand, if you face your whole hand toward V, so if we're starting, okay, how do I do this? This is going to be interesting drawing. Anyways, so you're facing your fingers toward there, and here's your thumb, just there, okay? If you're facing your fingers toward V, and you curl them toward W, so we're going to curl them this way, right, like in a counterclockwise direction, then your thumb is going to point, at this point, after you curl it, then it'll be in somewhat of like a fist form, right? I do not know how to draw a fist. So, anyways, we're curling our fingers, right? And the basic, the takeaway message here is that your thumb is going to point upward, okay? So that just says your V cross W, this vector here, our resultant vector, V cross W, is going to point upward as opposed to downward, okay? So that's how you determine which way it's going to point. We know it's going to be orthogonal to both of these, but we don't know whether it's going to be up in the positive z direction or the negative z direction, okay? All right, so the next thing I want to talk about, the next property, is this is called anti, so against or opposite, commutativity. So if you recall, the dot product was commutative, or it had commutativity, meaning that it didn't matter which order you dotted things. So this is a side note. V dot W is equal to W dot V, okay? It doesn't matter because we're just using all addition signs, right? But for the cross product, it's anti-commutative, meaning that if you switch the order for some reason, this is going to be, so if we do W cross V, this is going to be the opposite, so the negative of if you were to do V cross W. And that the negative sign just comes from, like I said, if you were to switch the order, do this instead. So the W cross V, then you write, you actually switch the placement of your components, right? So W would be in the middle of your 3x3. So you have I, J, and K. W would go here, the components would go there, and the components of V would go on the bottom row, right? As opposed to in the beginning how we had it like V was going here, the components were going there, and W were going there. So this on the left is equal to the opposite, so the negative sign of whatever you get from crossing V cross W. Okay? Alright, so the next kind of, well, it's not self-explanatory actually, but if you were to do this, work that out, if you were to cross one vector with itself, you would find that it equals 0. Okay? Or the 0 vector, whichever one you want to consider it. It'll just all turn out to be 0. Okay? Now for some last properties here. So number 6, sorry there are so many, but they're all pretty important. So number 6 is just saying that if we have a scalar, if we throw in a little like number like 2 or 3, if we throw that in with V and multiply it times that, if we have a scalar multiple crossed with W, we can basically move this scalar around anywhere. So that's the same as V cross times lambda W, okay? Or we could even just move it outside entirely. It doesn't really matter. Okay, it doesn't affect our final result. Okay? Alright, and our last property for today is going to be that of distributivity. Distributivity. There we go. Okay, so basically this is saying that if we have another vector here crossing with the sum of two vectors, what we can do is distribute this in and preserve the cross product. So via the cross product. So this is basically going to mean if you do U times V, we have to implement this cross V. Okay, so that's the first product. Then we're going to put an addition sign. And then when U is multiplied with W, it does so via the cross product as well. Okay, so we have two different cross products going on here because we distributed the U as well as the cross. Okay, so now on to a more geometrical application of the cross product.
To escape this man, life can get all up in your ass.